Hello there, let's start by talking a little bit about memory storage and communication. Consider how in every conversation you have, you transform a series of sounds into something with value. Without the meaning applied to it, the groups of hs, ahs, and those you say at the beginning of every greeting would merely be exactly what they seem like. A bunch of random sounds that when heard alone are nothing like the hello you heard at the beginning of this video. So why bother at all with this complicated communication tool called language? Without language, we would likely have a great difficulty creating society, much less the internet or even quantum computers as we know them today. Now, classical computers, that is what you might as well refer to as ordinary computers, operate using binary notation. You may or may not be familiar with this type of notation. It was first proposed by German polymath by the name of Gottfried Leibniz, who published the idea in 1703 under his work titled Explication de l'arithmétique binaire. Now, granted, this was largely for computational reasons, as the difference engine, widely considered the first mechanized computer, wouldn't be invented by Charles Babbage until 1822, and the first electromechanical binary computer wouldn't be invented until the late 1930s. Now, this binary notation utilizes strings of ones and zeros, and each position on these strings is what computer scientists refer to as a bit and provides a little bit of information. Now, individual bits that make up the code can only occupy one of two possible states, 1 and 0, and the computer, based on the possible series of bits that it can have, will have corresponding physical states. In terms of physical states, it can be interpreted as something as simple as a light switch going on and off. Now, qubits, on the other hand, are not quite as restricted to being one state or the other. Rather, they can be described as some combination of these states. Now, when considered the implementation of qubits, several properties arise that allow us to alter precisely how we approach problems in the real world. As noted previously, they are capable of simultaneously representing some combination of several states at once. Take, for instance, a simple 2-bit system. You have a total of 4 possible states. A classical computer is in one of these 4 states, but a quantum computer can be in all 4 at once through a characteristic known as superposition. Now, based upon this, let's formally define qubits to be a 2-dimensional unit ket composed of some real values. Ideally, given some orthonormal bases, we can represent this ket as a linear combination of these vectors. On the small scale, having a qubit able to be in multiple states at once doesn't seem to be too impressive of a detail. All 4 states at once, why not just purchase 3 more classical computers? Don't write it off quite yet. The difference becomes much more significant as the number of qubits we are considering increases. Consider a system with 32 qubits, which represent a total of approximately 4.3 billion states. Classical computers no problem can represent any one of these 4.3 billion states, but it takes quite a while to be able to cycle through all of them. Now, increase the number of bits involved to 64, and it could take a regular computer working at 2 billion states per second approximately 400 years to get through all of them. Now, quantum computers, on the other hand, have no issue processing all of these different states in a manageable amount of time. Now, in order to quote-unquote create a usable qubit, however, there have been several ways to approach the problem. The primary method for doing so has involved manipulating the spin of electrons. Now, one way researchers have approached this is by focusing on the outermost electron of the phosphorus atom. This electron has either spin up or spin down orientation when measured. In order to definitely know the electron's orientation, a magnetic field is applied to orient the electron's spin down, its lowest energy state. In order to change the spin of the electron, some energy must be applied. Here's where the issue of environmental factors comes into play. Now, at the room temperature, the excess of thermal energy can cause the electron to fluctuate out of control between spin up and spin down. Now, quite unfortunately, this leads to the loss of any useful information we get from the spin orientation of the electron. To avoid this, scientists must cool the temperature of the qubit to within a few fractions of a degree from absolute zero. Only recently, from around April 2020, have reports of a quantum computer been able to operate above 1 degree Kelvin been made, although it contained at most 2 qubits. Now, once the magnetic field is applied at exceedingly low temperatures, scientists are able to manipulate the spin of the electron. Now, to do so, scientists throw pulses of microwaves in the direction of the electron, and these microwaves are tuned to a very picky frequency, more specifically, typically the resonance frequency of the electron, approximately 45 gigahertz, kind of like how you might tune to a specific frequency on a radio. We can then pause this pulse at some point to quote-unquote pause this electron is suspended in a superimposed state. The phosphorus atom containing the electrons are embedded in silicon crystal, which is near a transistor. To effectively get information from these qubits, we utilize the transistors in order to read the state these electrons are in. Thus, through this process, we are able to construct, at its most fundamental level, a qubit. Now, naturally, this glosses over a number of technicalities regarding, for example, precisely how the extremely low temperatures may be achieved and maintained, etc. Nevertheless, this describes the basics of qubits as a whole. If you have any questions or want to learn more, feel free to check out the Q-munity Quantum Tech website. And as always, stay curious and keep on learning. Thank you!